The precise definition of a limit, part 2. We've looked at using absolute value inequalities to describe distance, and hopefully you feel more comfortable converting between the absolute value inequality and the graph. We've also looked at using absolute value inequalities to describe error, which is very similar, but instead of looking at the distance from x, we're looking at the distance from f of x. And again, hopefully you feel more comfortable converting between the absolute value inequality and its graph. Now we're going to combine the ideas of the distance from x and the distance from f of x in order to start looking at how to land inside of error bounds, which will bring us closer to the idea of a precise definition of a limit. First, we'll look at an example that is almost a real-world example, but you want to be careful because the graph is very made up, because I couldn't find any information on the actual process to manufacture a baseball bat, just information on baseball bats. So you've been hired by a factory that creates baseball bats from lumber. So we input lumber and we output baseball bats at this factory. The average length of a baseball bat is 30 inches, but there are people who will need a baseball bat that is anywhere between 4 inches shorter and 4 inches longer. So the goal is 30 inches, but we're okay if it's 4 inches shorter or 4 inches longer because somebody will buy that baseball bat. The company wants to know what size lumber they should use to try to produce baseball bats that are 30 inches long with a maximum error of 4 inches. So that means that they're aiming for this 30 inches, but they're okay if we're 4 inches shorter or 4 inches longer. So we're okay with 34, and we're okay with 4 less than 30, which is 26. Which I didn't quite draw very well. There we go. And this creates an error band. So we know that we are okay if the distance between f of x and 30 is less than 4 inches. But we want to know that when we're falling within that error bound, what are the lengths of lumber that will actually get us there? So we want to make sure that no matter what lumber we're putting into this factory, we're getting a length of bat that we're okay with. So let's look at where these error bounds intersect with our function. And if we do that, we see that 30 inches of lumber will give us 26 inches of bat. It's probably not the right way to say that. And 40 inches of lumber will produce a bat that is 34 inches long. And as long as we're between those two lengths of lumber, we're going to fall inside this band here. And we want a good way to describe that band, so we'll find the center. So halfway between 30 and 40 is 35, and the distance between 30 and 35 is 5, and between 35 and 40 is also 5. So we're okay if the length of lumber x and the distance between that x and 35 is a maximum of 5 inches. So as long as lumber is a maximum of 5 inches away from 35, then we know that we're going to fall within that band. Because if we had a length of lumber that was 20, because that'll already have a line, that would mean that we landed over here. And that is not inside our error band, so that doesn't help us. But if we had a length of lumber that was like 36, we'd still fall within our error band. So we're happy there. Of course, we do want to get as close to 30 as possible. That's a little hard to erase. And if we look at that, So if we go to 30 and we trace down, we see that 35 as our length of lumber should output a bat that is that goal size of 30 inches long. So what we can kind of see is that our goal here is that the limit as x approaches 35, so as the length of lumber is approaching 35, we hope that f of x, the length of our bat, is approaching 30. So we're saying that as we're falling within our band here, this distance from x, we should also fall within this band here for f of x. Now let's say we have some function f of x and want to show that the limit as x approaches 3 of f of x is equal to 2. In this case, the distance delta from x to 3 could be represented as the absolute value of x minus 3. And the error from f of x to 2 would be the absolute value of f of x minus 2. Just like we've seen before, that's how we use absolute values to show distance. And our goal in this case is we want to show that the distance from f of x to 2 is less than 0.5, so that's the maximum error. And if that's true, then there's a distance delta from x to 3 that guarantees when x is less than that distance from 3, f of x will be less than 0.5 from 2. So algebraically, we want to show if delta, the distance from x to 3, is less than delta. So if the distance from x to 3 is less than delta, then the distance from f of x to L is less than 0.5. So we're given our epsilon, that distance or error for f of x, and we want to find our delta. So let's look at this same graph here for f of x, but with a little more room to work with. Okay, so again, we're trying to show that if the distance from x to 3 is less than delta, then the distance from f of x to 2, or error between f of x and 2, is less than 0.5. So let's check our f of x first. So we see that we're centered at 2, which is great in our graph, so that's our limit that we're approaching. And the distance epsilon, or error epsilon, between 2 and 2.5 is 0.5, just like we wanted. And the error between 2 and 1.5 is also 0.5, just like we wanted. And luckily for this graph, we see where these bands intersect with our function, and we see the x values that would give us each of these outputs. So now we just need to find the distance between these delta bands. So the distance between 2.6 and 3 would be 0.4, and that just comes from 3 minus 2.6. And the distance between 3.8 and 3 is 0.8, which just comes from 3.8 minus 3. And unfortunately, these are different, so we're going to have to do a bit of thinking here. So our goal is to make sure that whenever we're one of these distances from 3, the output will fall within this error bound. So let's see what happens if we chose 0.4. So we already know the left bound for 0.4, that's the 2.6. But let's look on the other side for the right bound. 3 plus 0.4 would give us 3.4. And if we look at the output for 3.4, that's not a very straight line. Well, it's still not very straight, but I tried. We see that that output falls within our error band. So 0.4 would work for delta. Now let's see what happens if we chose, and I'll check up here so there's a little more room. Let's see what happens if we choose 0.8 for our delta. Well, we have our right bound, but we still need to look for our left bound. So that would be 3 minus 0.8, which would give us 2.2. And if we look at the output for 2.2, we see that when we input 2.2, we do not fall within our error bound. So unfortunately, a delta of 0.8 would not work. So when you're forced to choose between two deltas, you want to make sure you're always choosing the smaller delta. So the delta in this case that guarantees that we fall within our error bound is 0.4.